Night in the Amazon rarely feels still, but there are moments, thin ones, when the forest holds its breath. Under the trembling canopy, moonlight breaks in fractured bands, striking only what the leaves allow. Everything else dissolves into warm darkness, a humid world of breath, sweat, and slow-moving shadows. It is inside this world, almost invisible against the bark and vine lattice, that the assassin bug begins its nightly search. Its movement is delicate but deliberate, each step designed for silence. This insect is not built to chase, it is built to infiltrate. It thrives in moments when the jungle's giants are asleep, when even the predators are vulnerable. The camera catches it climbing onto a low branch that droops over a resting mammal, a small opossum curled into its own fur, oblivious to the approaching danger. The bug pauses, antennae flicking once, twice, tasting the air. Warm carbon dioxide pulls it downward toward the animal's face like a scent trail carved in 3 dimensions. For a creature barely the length of a fingernail, this heat signature is a beacon. It crawls across fur with the confidence of something that understands perfectly just how defenseless its host is. It knows the opossum won't wake. Its survival strategy depends on it. What happens next is almost surgical. The assassin bug presses its rostrum, its needle-like mouthpart, against the skin. But instead of piercing immediately, it delivers a minute droplet of saliva infused with anesthetic compounds. These proteins are highly refined, shaped by millions of years of trial and error. Their job is simple: turn pain off. Within seconds, the skin numbs, and only then does the rostrum slide inside. There is no twitch, no recoil. The bug might as well be drinking from a plant stalk for all the reaction it triggers. It begins to feed, drawing up warm blood in rhythmic pulses that match its internal pump. Under magnification, you would see red cells moving through the transparent channel as though pulled by some hidden tide. On its own, this act is ordinary. Countless insects across ecosystems drink blood. But the assassin bug carries something that rewrites the meaning of the bite entirely. Inside its gut, within its own digestive tract, live parasites. Trypanosoma cruzi, the single-celled organism responsible for Chagas disease. This isn't a virus that burns hot and fast. This is a parasite built for patience. It wants long-term residency inside a host's tissues. It wants years, not minutes. The transmission is a quiet tragedy. The bug doesn't inject the parasite directly. Instead, the infection begins in a way that seems almost absurdly indirect. The insect defecates as it feeds. The parasite is not in the saliva, it is in the feces, microscopic, unnoticed, and perfectly positioned on broken skin. The host, half asleep, may twitch or rub the spot. A claw, a tail, even a passing leaf can smear contaminated material into the tiny wound. That moment, small, accidental, invisible to the camera, is the real bite. This is the entry point for a slow, systemic collapse. Once inside, Trypanosoma cruzi behaves like an infiltration unit. The parasites travel through blood vessels but avoid confrontation with the immune system whenever possible, slipping into muscle tissues and hiding inside cells. This is where their strategy becomes devastating. They transform the host's cells into incubators, multiplying quietly. Over months or even years, the damage accumulates. Heart tissue slowly stiffens. Electrical rhythms destabilize. The digestive tract begins to dilate. A once healthy animal becomes weaker without understanding why. Slower reflexes, irregular breathing, sudden collapses. What started as a painless nighttime bite can turn into heart failure long after the insect has moved on. In a forest full of jaguars, caimans, and venomous snakes, the assassin bug delivers a kill measured not in seconds, but in seasons. It is a long-game predator, a biological time bomb that rewrites what predation looks like. Most hunters rely on speed or strength. This insect relies on biology's quiet erosion. As dawn approaches, not everything remains unaware of this threat. The assassin bug is toxic in a different way, its reputation. Predators that rely on taste-based evaluation, birds, lizards, small mammals, learn within a single encounter that these insects are not worth the risk. The bug's defensive strategy involves releasing foul secretions when threatened, compounds so offensively bitter that many predators immediately spit them out. Over time, this becomes instinctual avoidance. A tanager that once sampled an assassin bug will never attempt it again. A gecko that bites down on one may recoil with such force that it falls from its perch. Evolution writes these lessons quickly. The jungle does not reward repeat mistakes. Some predators, especially birds, have learned an even sharper trick. Instead of eating the bug, they shake or peck it until it bursts, avoiding the worst flavors and leaving behind only the nutritious parts. It's a calculated technique, but even then, many choose to avoid assassin bugs entirely. The risk is simply not worth the reward when easier prey fills the forest. The ecosystem around the assassin bug adapts in subtler ways as well. Certain mammals groom intensely around the face and mouth, where bites are most common. Species with thicker fur around sensitive regions show lower parasite loads. Even the nightly resting positions of animals shift based on insect pressure. Bats roost in patterns that reduce exposure. Rodents choose micro-habitats with cooler airflow that confuses the bug's heat-seeking instincts. These changes are the result of generations of interaction, a constant negotiation between hunter and hunted. Yet despite all these defenses, the assassin bug survives and thrives. It does not need large numbers. A single infected individual can set off chains of illness across multiple species. In some regions of the Amazon, up to 40% of mammals carry signs of chronic infection. The parasite becomes woven into the biology of the ecosystem, influencing behavior, population size, and even predator-prey dynamics. A jaguar weakened by chronic heart inflammation may fail a hunt it would normally win. A slow-moving capybara might lose the sprint to the water's edge. The parasite's reach extends far beyond the initial bite. This is the hidden layer of the forest, the threats that don't roar or thrash or strike, but instead seep into the bloodstream and wait. Under the leaf litter, behind loose bark, inside thatched nests, assassin bugs continue their quiet patrols. They don't look dangerous. They don't sound dangerous, but they embody a deeper truth of the Amazon. Not all predators need to be strong, large, or fast. Some only need to be unseen. As the camera pulls away, the jungle wakes to its usual chaos. Monkeys calling, insects droning, river water shifting through roots. The opossum cleans its face, unaware of the microscopic threat already inside. It looks healthy. It is healthy. For now. But the timer has already started. and somewhere within its tissues, the parasite begins its slow, irreversible work. Dusk in the Amazon always feels like an opening act. The heat finally loosens its grip, the canopy exhales, and animals begin migrating toward water with the confidence that the worst of the day is behind them. But in the stagnant pools scattered between buttress roots and fallen branches, something else is waking. The surface tension quivers with faint ripples, larvae rising for air, pupae tumbling just beneath the film. These miniature life rafts are nurseries for the deadliest lineage the rainforest has ever produced. As the light softens and the humidity rises, they begin to climb, break the surface, and unfold into the thinnest, most fragile killers in the entire biome. The first mosquito of the evening is rarely noticed. It lifts from the water as though carried by the air itself, wings vibrating at a frequency too high for most human ears. Its entire weight is less than a grain of sand, yet the ecological gravity it holds over the Amazon is staggering. Jaguars, caimans, bushmasters, giant centipedes, none of them come close to the mosquito's yearly kill count. Predators roar, hiss, and strike. Mosquitoes maintain a kill rate through quiet persistence, through microscopic agents carried in their saliva, and through a hunting strategy built around precision chemistry rather than brute force. The camera follows one female as she hovers above a dark pool, her body angled like a compass needle seeking direction. She begins sampling the air, not through sight. Her vision is crude compared to almost anything else in the forest, but through a suite of sensory receptors that can detect exhaled carbon dioxide from over 20 meters away. CO2 signals life, and life signals blood. The molecule spreads in a faint, invisible plume from mammals, birds, and reptiles, moving with the wind like a ghost trail that only she can read. When she turns toward it, her entire body becomes an antenna, maxillary palps picking up chemical ratios, antennae tuned to heat gradients, and the tiny chambers in her legs sensitive to moisture. The result is a flight path that seems erratic, but is actually mathematical. She is tracing inhalations, sweat, temperature, and humidity like a predator following a scent map. This particular CO2 plume belongs to a woolly monkey stretched along a branch above the swamp. He has climbed here to avoid ground predators, unaware that he has flown straight into the vector field of something far more insidious. The mosquito lands on the branch first, testing the vibration. The monkey is calm. She inches closer. With each step, she translates thermal radiation through her antennae, tiny heat signatures blooming under the fur where blood vessels run close to the skin. To a mosquito, a mammal doesn't look like an animal. It looks like a living map of capillaries. The moment she touches the monkey, her feet taste chemicals in the skin that confirm what she already knows. Blood is extremely close beneath the surface here. But blood is hard to access through fur, so she searches until she finds a warm patch near the eyelid where hair thins. Then she begins her mechanism of attack, not with a sting, but with a tool set that looks simple from the outside and is shockingly complex inside. Her needle is actually a bundle of 6 mouthparts housed inside a sheath. She flexes the sheath aside like drawing curtains, revealing serrated stylets designed not to puncture skin, but to saw through it. This is the part most people never understand. Mosquitoes don't stab. They cut. Micro teeth move back and forth so fast that the entry feels like nothing at all. As soon as the stylets enter, she releases a cocktail of proteins, anticoagulants to keep the blood flowing, vasodilators to widen vessels, mild anesthetics so the host never feels the intrusion, and, depending on the species, parasites or viruses that can collapse organs, scramble immune systems, or inflame the brain. The woolly monkey stirs. He feels a vague irritation, but nothing that triggers alarm. The mosquito's saliva has neutralized the body's immediate defenses. Inside his bloodstream, however, a new chain of events has already been set into motion. Some mosquitoes deliver malaria parasites, Plasmodium species that split their life cycle between insect and vertebrate. Others deliver arboviruses like dengue, yellow fever, Zika, or Mayaro. Each has its own strategy, but the outcome is similar: fever, hemorrhage, neurological dysfunction, organ failure. The most devastating part is that the monkey may not show symptoms for days. During that time, other mosquitoes will land, feed, and leave, carrying the parasite to the next host. A single infected mosquito can trigger an outbreak that reshapes entire troop structures. The camera lifts above the swamp just as more mosquitoes join the cloud. Their flight resembles a vibration more than a swarm. Thousands of individuals, each following chemical cues like data packets traveling through an invisible network. They aren't coordinated in the way bees or ants are, yet their collective impact rivals any colony. Few predators bother with them. Dragonflies catch a handful. Bats snatch them when available. Fish eat larvae by the thousands. But these losses barely dent their numbers. They reproduce explosively because they need to. Mortality is part of their design. They survive by overwhelming the ecosystem with sheer scale. As darkness deepens, the swamp becomes a theater of invisible warfare. Capuchin monkeys slap their shoulders and flanks, creating rhythmic thuds in frustration. Tapirs retreat into deeper water, submerging their heads whenever possible to escape the onslaught. Even jaguars, apex predators built for ambush and brute force, twitch their ears and shake their heads as mosquitoes probe the thin skin inside. For humans, the effect is immediate and merciless. Those who venture through the low wetlands at night often emerge covered in bites, unaware which particular sting delivered which particular pathogen. Over generations, mosquitoes quietly redraw population boundaries across the Amazon. Troops of primates decline or shift territory during bad malaria years. Bird species lose hatchlings to fevers that sweep through nest sites. Human villages endure waves of arboviral outbreaks that can reshape settlement patterns and hunting routes. Even predators feel the downstream effects. Fewer monkeys mean fewer prey for harpy eagles. Fewer deer mean jaguars travel longer distances, altering territorial conflicts. These changes ripple outward like aftershocks from an event no larger than a speck of ash. What makes mosquitoes especially dangerous is their indifference. They do not intend to kill. They do not benefit from the death of their hosts. They are simply vessels, mobile syringes carrying genetic passengers that use them as couriers. The ecosystem doesn't fear mosquitoes because they're tiny. It respects them because they're portals. Each bite is an invitation for another organism to enter, hijack, multiply, and spread. Yet mosquitoes also play roles the jungle cannot function without. Their larvae filter nutrients from stagnant water, accelerating decomposition and keeping pools from stagnating into toxic pits. Birds and bats rely on them for calories during breeding seasons. Fish fatten on swarms of wriggling larvae. Even the flowers of certain plants benefit from the incidental visits of nectar-feeding mosquito species. The paradox is that the Amazon's most lethal killers are also fundamental to its health. Back at the swamp, the woolly monkey climbs higher, uncomfortable from the bite, but unaware of the microscopic storm circulating inside him. The mosquito, lightened by the blood meal, drifts into the air again. Her abdomen glows faintly red in the dying light. She will rest for a day or two while eggs develop. Then she will return to the water's edge and tap her abdomen to the surface film, releasing new life into the world. Hundreds of larvae that will dangle upside down from the water tension like an inverted crowd. The cycle is relentless. The jungle breathes. The mosquitoes rise. The next wave takes flight. And in this system, towering trees, roaring predators, ancient rivers, these insects remain the quiet, persistent force that kills more animals than anything else. They do it without strength, without venom glands, without size. They do it because evolution gave them a perfect trifecta: mobility, chemistry, and the ability to weaponize disease. In the Amazon, death often announces itself with a hiss or a snap or a splash. But sometimes the deadliest blow is delivered by a creature lighter than a raindrop, arriving in silence, leaving the faintest mark, and disappearing long before the real damage begins. Rain in the Amazon never merely falls. It detonates across the canopy in sheets that rattle leaves, drum on hollow trunks, and soak the forest floor in seconds. When the storm finally pulls back, the world beneath the trees glows as though lit from within. Every leaf carries a mirrored sheen, every vine gleams like a polished rope, and the air itself feels dense enough to touch. In this newly washed landscape, movement becomes more obvious. Tiny breaths, shifting droplets, small pulses of color vibrating against the monochrome green. It is here, in this post-storm clarity, that the poison dart frog steps into view, perched on a broad bromeliad leaf still trembling from the downpour. At first glance, the frog's size borders on absurdity. Some species stand no larger than a thumbnail, delicate enough that the weight of a falling raindrop could nearly topple them. And yet, pound for pound, few animals on Earth command such biological authority. Their bodies are constructed around a warning: neon yellows, acidic greens, cobalt blues, and searing reds trace across their skin in patterns that seem hand-painted by an artist with a vendetta. This isn't decoration, it's a promise. In a forest where camouflage often means life, poison dart frogs do the opposite. They advertise. The frog shifts, revealing a flash of electric blue along its flank. Camera close-ups catch the granular texture of the skin, as if each pigment cluster were carved into place. Embedded within that vibrant surface is chemistry evolved for one purpose: to shut down living systems. The toxins are alkaloids, molecular weapons. The frog does not manufacture itself, but instead steals, refines, and stores from its prey. Ants, beetles, mites, tiny arthropods that spend their lives accumulating plant-derived toxins become the source material. The frog's digestive system strips these compounds, concentrates them, and loads them into its skin glands. The result is a chemical library of astonishing potency. Some species carry enough toxin to kill dozens of birds. Others can drop a large mammal. The golden poison frog, infamous even among its kin, contains enough batrachotoxin to kill multiple humans outright. What these toxins do at the cellular level is both elegant and catastrophic. Nerves fire by opening and closing sodium channels. microscopic gates that allow pulses of electricity to cascade along neurons and muscle fibers. Poison dart frog alkaloids hijack these channels. Some lock them open, causing uncontrolled firing that leads to paralysis. Others lock them shut, silencing nerves entirely and halting muscle contraction. The heart, a pump that relies on precise electrical timing, becomes the prime casualty. Its rhythm stutters, falters, then collapses under the chemical assault. Death can follow in minutes. The frog does not need to bite, claw, or even move quickly. Contact is enough. A predator brushing the frog with its tongue can receive a dose that shuts down its body before it understands what happened. Birds that attempt to strike often recoil mid-attack, shaking their beaks violently as the first numbness spreads. Snakes learn faster. Individuals that survive a poisoned meal, rare as that is, develop an instinctual aversion to the frog's colors. Their pupils dilate, mouths gape defensively, and they slide away with urgency rarely seen in reptiles. Evolution does not treat those who ignore warnings kindly. The forest remembers these warnings in countless small behaviors. Juvenile birds imprint the frog's patterns after witnessing a sibling fall from a branch, paralyzed. Mammals that forage near streams learn to avoid certain mossy logs where dart frogs often sit to absorb heat after rain. Even insects, though not directly threatened, alter their routes to avoid areas where frog populations are dense. It is not fear they sense, but chemical signals, barely perceptible alkaloid residues on wet leaves that trigger avoidance in species tuned to detect them. Yet with all this raw lethality, the frog's life is not one of invincibility. It must thermoregulate constantly, shifting between sunlit perches and shaded roots to maintain its narrow temperature range. Its skin dries quickly, making moisture a matter of survival. Its eggs, laid in hidden pockets of water, depend entirely on the placement of the parents. In many species, the males stand guard over the clutch, keeping them hydrated with daily trips from nearby pools. When tadpoles hatch, the female transports them one by one on her back to water-filled plant cavities, bromeliads, tree hollows, even spider-made cups. This parental care, rare for amphibians, produces surprisingly low mortality despite the forest's predators. The frog's toxin does not harm its offspring. Tadpoles are born vulnerable, unarmed, and soft-bodied. They only begin to accumulate alkaloids once they transition to a diet of toxic arthropods. This creates a window of danger where the young must avoid predators without their chemical shield. Here, parental behavior becomes essential. Many species feed their tadpoles unfertilized eggs, nutrient-rich spheres delivered at intervals to sustain growth. These eggs contain trace alkaloids, priming the tadpoles with low doses that begin the process of toxin resistance. It's an evolutionary apprenticeship in chemical warfare. As for the adult frogs, their vivid colors aren't simply warnings, they are also thermoregulatory tools. Bright skin reflects and absorbs heat differently across wavelengths, allowing frogs to maintain optimal temperatures while avoiding overheating in the sun. Researchers observing dart frog colonies note that individuals adjust their body angle to maximize heat intake while minimizing UV exposure. Their colors, paradoxically, help them survive both predators and the environment. The camera shifts now to a lowland clearing where indigenous hunters prepare blowgun darts beside a small fire. The association between dart frogs and hunting tools is ancient and precise. Only a handful of species carry toxins strong enough to be used in this way, and even then, only individuals from specific valleys or microhabitats produce the highest potency. Hunters gently heat the frog over the fire, not to kill it, but to stimulate toxin release onto wooden splints. The process is respectful, ritualized, and controlled. The frog is released afterward, unharmed but temporarily emptied of its chemical store. The darts, once tipped, become extensions of the frog's biology. A single scratch from such a dart can drop a monkey mid-leap or halt a peccary's charge in seconds. What makes this partnership extraordinary is how deeply it ties human survival to amphibian ecology. When frog populations fluctuate, hunting success changes. When forests are disturbed, toxin potency drops because the insects that supply the alkaloids disappear. This relationship reveals how dependent even apex-level human hunters can be on creatures barely larger than a coin. But toxins come with vulnerabilities. Many dart frog species rely on specific prey to maintain their chemical defenses. When habitat fragmentation reduces arthropod diversity, frog toxicity declines. Captive-bred dart frogs, fed non-toxic insects, lose their ability to produce poisons entirely. Their skin becomes harmless, proof that their power is borrowed, not innate. In the wild, however, their chemical arsenal remains intact, and predators know it. One strike teaches everything they need to know. A hawk circles above the clearing. It spots the frog's neon signature and dismisses it instantly. The frog shifts slightly, water droplets rolling off its back like mercury beads. Its throat expands softly as it exhales, singing a call that sounds more like a tiny vibration than a true voice. This is a territorial display, a declaration of presence. It stands openly, confidently, because almost nothing in this forest will challenge it. Almost. There are rare specialists, snakes like the Amazonian frog-eating species Limnodophis epinephalus, immune to certain alkaloids. Their immunity doesn't come cheaply. Their physiology is geared toward neutralizing or compartmentalizing toxins that would cripple other predators. These snakes track the frogs visually, using bright coloration as a beacon instead of a warning. For a brief moment, the balance shifts and the frog becomes prey again. But even here, the risk is real. Immune does not mean invulnerable. A mistake in dosage or species can still kill. Back on its leaf, the frog lifts itself slightly, absorbing warmth. Rain begins again, soft at first, then relentless. Droplets hammer the canopy, run down the leaves, and bead across the frog's skin. But it does not hide. It stands exposed, neon colors blazing in the grey light, a living contradiction in a world built on stealth. Evolution has armed it with a simple message written in color: touch me and die. For most of the Amazon, that warning is enough. Deep beneath the Amazon's surface world, the world of bright leaves, neon frogs and sun-drunk insects, there is another Amazon entirely. It exists in darkness, in the hollows where tree roots twist like knotted bone, in the tight chambers under decaying logs, in the crevices where stones meet damp soil. Down here, light does not travel freely, sound moves in muffled vibrations, and the air feels cooler but far more claustrophobic. This is a territory built for quiet hunters, and few claim it as effectively as the black widow spider. The first glimpse is rarely the spider itself. Instead, the camera catches a glint of something artificial-looking, threads stretched with improbable geometry, sticky lines crisscrossing a pocket of shadow. Black widow webs are never symmetrical masterpieces like orb weaver designs. They are disorder made functional. A three-dimensional snare, a chaos trap. Sticky anchors run in every direction, designed to entangle anything that brushes against them. An accidental footstep by a beetle, the wing beat of a moth, even the probing leg of another spider. These lines vibrate differently depending on the weight, the struggle, the rhythm of contact. To the widow, each vibration reads like a signature. She emerges only when she chooses. Her body is small, matte black, barely reflective even when the camera pushes close. Only the red hourglass beneath her abdomen reveals her as something unmistakable. But most of her life, that marking remains hidden, tucked under her as she works from the shadows of her tangled home. She doesn't rely on color to warn. Her warning is chemical, and it lives inside her fangs. A small lizard, nothing more than a hatchling, approaches the root hollow, tongue flicking at the scent of beetles trapped inside. It steps once, then again, brushing the outer web. The vibration transmits instantly, and the widow freezes. She feels the tremor through her legs, evaluating the amplitude. Too large, too heavy. She won't try to overpower it directly. But she doesn't need to. Her web is built to transform size into vulnerability. The lizard moves deeper, its forelimbs snagging on a secondary line that adheres with painful tenacity. The spider advances now, silent, precise, every movement a calculation. When she reaches the edge of the struggle, she doesn't rush the kill. Instead, she manipulates the web, tightening structural threads to restrict the lizard's range of motion. The more the animal thrashes, the more the fibers constrict. The lizard's muscles push and fail, until its breathing accelerates. In the low light, its movements look frantic. To the spider, they simply mean opportunity. She approaches from the side, climbing onto the lizard's tail, where scales offer some protection, but not enough. The strike is fast, barely a tap. Her fangs penetrate at an angle that delivers venom directly into soft tissue. The lizard jerks, twisting violently, but its doom is already inside it. Widow venom is not designed for pain at first contact. It is designed for systemic collapse. The toxin, latrotoxin, is a neurochemical saboteur. It hijacks calcium channels in nerve endings, forcing them open and flooding them with ions. Nerves that normally fire only in response to specific signals begin firing uncontrollably. The body's communication system becomes a static-filled radio blast, nonsense signals firing every muscle at once. The lizard's limbs tremble, then convulse. Its jaw clamps shut uncontrollably. Its chest muscles spasm in rapid waves that mimic panic, even though the animal is no longer conscious of its surroundings. Muscles burn internally from the overexertion, and the calcium imbalance begins destroying the very cells meant to sustain movement. To the spider, this is progress. She waits. Black widows do not need immediate death. They need stillness. As the venom continues to spread, the lizard's spasms grow weaker, replaced by a terrifying stiffness known as tetany, muscles locked in place, unable to relax. The respiratory system is one of the last to fall. The diaphragm contracts again and again, shallow and uneven. If the lizard were larger, it might survive the night. But small animals collapse far earlier. Within minutes, the chest stops. Silence returns to the hollow, broken only by the faint hum of distant insects outside. Now the widow closes in. Her fangs inject digestive enzymes that liquefy tissue under the skin, turning muscle into nutrient-rich slurry she can drink over hours. She feeds slowly, methodically, taking only what she needs. The rest of the carcass will dry into a shell that hangs in the web like a warning for anything unlucky enough to stumble near. This entire process, brutal in its efficiency, stands in stark contrast to the widow's appearance. She is tiny, easily overlooked, easily crushed, fragile enough that a single raindrop could knock her from her web. Yet her venom is engineered for scale. It affects birds, mammals, reptiles, amphibians, virtually every vertebrate with a calcium-regulated nervous system. Even animals much larger than her feel the internal fire she releases. Surviving a widow bite is possible for many species, but survivors are shaped by the memory of it. A small mammal bitten once may avoid root hollows for the rest of its life. Snakes that survive an encounter develop an aversion so deep it alters their hunting patterns. Even predators capable of killing widows, like certain wasps, approach with meticulous care, immobilizing the spider instantly to avoid any chance of venom exposure. The fear is not of the spider's fangs, but of the aftermath. Hours of cramps like metal bands tightening around the ribs, waves of abdominal contractions that mimic childbirth, chest pain so intense that cardiac stress becomes a threat even without direct venom targeting the heart. In humans, the venom causes a syndrome known as latrodectism: sweating, tremors, rigid abdominal walls, skyrocketing blood pressure, and pain radiating through the back and chest. People describe it as their muscles being lit from the inside. The phrase is not poetic, it is accurate. It is the same cellular mechanism the lizard experiences. Too much calcium, too many nerves firing without order, too much muscle contraction without pause. Yet despite all this, black widows remain misunderstood. They are not aggressive hunters. They are ambush spiders, relying on stealth rather than confrontation. They bite only when threatened, and even then, they ration their venom carefully. Producing such potent chemistry is metabolically expensive. A widow prefers to immobilize prey precisely, not waste her arsenal on a fight she doesn't need. Her presence is a lesson in ecological disproportion. Size means nothing when chemistry does the killing. Mobility means nothing when a single bite can turn a larger animal into a locked statue. Even predators built for crushing or tearing hesitate around a creature that weighs less than a dried leaf. The camera returns to the hollow. The feeding is nearly done. The spider retreats into her web's interior architecture, the carcass of the lizard now a pale husk suspended above the soil. Raindrops begin to fall again outside, tapping the canopy like distant applause. In the darkness, the widow resets the trap, tightening threads, repairing breaks, weaving new snares. She works with the patience of a creature that knows the forest will deliver another victim soon enough. Another beetle, another froglet, another hatchling exploring the wrong crevice. In a jungle built on strength, speed, and bright displays, the black widow thrives through restraint. No roar, no color, no chase. Just silence, venom, and the certainty that any creature, no matter its size, can be undone by a spider no heavier than a raindrop. The fire she unleashes burns inside muscles, not outside them, and in a forest full of predators, that is a power few ever forget. In the Amazon's flooded forests, where the river lifts itself into the trees and every shadow can be mistaken for a living thing, the boundary between land and water disappears. Branches sag under the weight of moss soaked in black water. Fish drift between submerged roots. Birds cut across mirrored surfaces that reflect only broken sky. And beneath it all, beneath the silence, the glare, the drifting leaves, something lies in wait that the forest itself seems reluctant to acknowledge. The anaconda does not swim so much as it dissolves into its surroundings. Its olive scales break the surface tension with barely a ripple. Mud, algae, and the sheen of tannins blend across its skin, turning the world's heaviest snake into a contour of the riverbed. Only the eyes and nostrils remain visible above the waterline, positioned on the top of the skull like periscopes. The rest of the body, thick, muscular, and impossibly long, coils in a slack spiral beneath the dark water. As the camera moves through the channel, every submerged branch looks like a limb, every fallen vine like a tail. But the anaconda is not rooted. It is waiting. A capybara herd approaches the flooded margin, nibbling at plants that grow in the shallows. Their movements are confident, practiced. They are excellent swimmers, stronger than most animals their size, capable of diving deep to evade predators. But confidence is not armor here. Among the reeds and submerged driftwood, the anaconda senses the faint pulses of movement, pressure waves that travel through the water and into its jawbones. These vibrations carry information: size, direction, rhythm. They might as well be announcements. The capybara steps into a slightly deeper channel and pauses, ears flicking. That hesitation is all the snake needs. The strike is not cinematic in the traditional sense. No dramatic lunge, no eruption of scales from the water. It is more like a switch flipping. One moment the channel is empty. The next, something massive folds upward and sideways, seizing the capybara in a burst of coils. There is no roar, no scream, only the violent displacement of water and the muffled grunt of air leaving lungs. Many imagine constriction as suffocation, as if the snake were choking the breath out of its prey. But the reality is far more precise and far more lethal. The anaconda is not cutting off air. It is shutting down circulation. Each coil tightens with the capybara's exhale. With every breath the animal releases, the coils cinch tighter, preventing the next inhale from fully expanding the chest. But the real devastation happens deeper. Veins collapse first. These vessels are low-pressure pathways responsible for returning blood to the heart. Under the snake's pressure, they flatten like drinking straws under a boot. Blood can leave the heart, but it cannot return. Within seconds, pressure builds. The heart pumps desperately into a system that can no longer cycle. Organs begin to starve. The liver swells. The kidneys darken. The brain enters an electrical panic as oxygen declines. The capybara thrashes once, then twice. Then the movements shift into chaotic spasms as tissues lose coordination. The snake feels all of this, not visually, not by sound, but through the contact of coils. Its muscles function like an array of sensors. Every heartbeat transfers a vibration into the snake's body. When the heartbeat weakens, the snake tightens. When the heartbeat falters, it tightens again. And when the heartbeat stops, the snake knows the kill is complete. This is the horror of the anaconda's method. There is no wound, no tearing, no blood. From the outside, the prey looks intact. No gore, no broken bones, only a stillness that seems almost peaceful, until one realizes that the animal was shut off from within. Constriction is not strangulation, it is internal collapse. Birds fare no better. When herons or jacamars come too close to a half-submerged anaconda, the strike is swift. The bird's bones crack easily, but the snake doesn't rely on fractures. It coils anyway, wrapping delicate bodies in loops thicker than the prey's entire wingspan. The coils do not crush with brute force. They crush with pressure that mimics catastrophic changes in blood flow. The result is immediate blackouts. Many birds die within seconds, their hearts unable to overcome the circulatory blockade. Caimans present a different challenge. Armored, strong, and equipped with jaws that can shear limbs, they are not easy prey. And yet, juvenile caimans are among the anaconda's regular meals. The snake approaches them differently, slower, more deliberate, often waiting until the young caiman rises to breathe. The strike clamps the neck or torso, dragging the reptile off balance. The coils follow not like ropes, but like hydraulic machinery. The caiman thrashes violently, creating waves that rock entire patches of the channel, but the snake holds with inexhaustible endurance. Caimans do not need much oxygen. They can hold their breath for long periods, but they still rely on blood flow. Their thick skin offers no protection from circulatory shutdown. Once the veins collapse and the heart begins to fail, even these mini crocodiles succumb. The anaconda maintains pressure until it feels the pulse fade to nothing, then holds longer still. A margin of safety evolution has perfected. Throughout these hunts, the surroundings remain eerily calm. Frogs continue croaking nearby. Fish move past cautiously. The water surface closes again as if nothing happened. In this environment, silence is not the absence of violence, it is the camouflage of it. The anaconda itself must navigate a precarious existence despite its power. Its metabolism is slow. After consuming a large meal, capybara, caiman, or even a deer, it may not feed for weeks or months. During this time, it becomes vulnerable. Digestion demands heat, so the snake must bask in shallow water, warmed by the sun. This behavior exposes it to other predators, jaguars that patrol the banks, giant otters that treat snakes as competitors, even large caimans that see opportunity in a sluggish, digesting body. To avoid these dangers, the anaconda uses the flooded forest as refuge. When water rises during the rainy season, the snake moves upward with it, navigating through submerged branches, finding quiet pockets where heat and safety builds. As it digests, its body swells visibly. The skin stretches but never splits. Its musculature redistributes weight to prevent drowning during long periods of inactivity. But when the snake is hungry, when the coils are empty, and the forest is full of sound, the anaconda becomes one of the most efficient predators on the continent. It does not rely on speed, it relies on positioning. It does not rely on venom, it relies on pressure. Its weapon is physics engineered through muscle and patience. One of the most chilling aspects of anaconda predation is the lack of external trauma. Autopsies of prey show intact skeletons, undamaged lungs, and no puncture wounds beyond small tooth marks that do not bleed heavily. Instead, the organs reveal the truth: hemorrhaged veins, ruptured capillaries, fluid accumulation, and tissue hypoxia. The animal did not die because it could not breathe. It died because its blood could not move. Constriction is a form of biological sabotage, and the anaconda wields it with precision. The chapter closes as the camera returns to the channel. The anaconda releases the capybara's limp body and holds it gently in its coils, adjusting position before guiding it into its mouth. The process is slow but unstoppable. Ligaments stretch, jawbones hinge, muscles ripple in waves. The snake consumes the prey whole, swallowing not just a body, but the last trace of movement that disturbed the channel's stillness. Then, just as silently as it appeared, the anaconda sinks beneath the water. The channel looks empty again, but in this flooded world, nothing is ever truly gone. Something is always watching. Something is always waiting. In the dim light of late afternoon, when the Amazon's surface takes on a bronze sheen and the forest above sinks into heavy silence, the river's side channels become almost unnervingly still. These shaded oxbows, wedged between leaning palm trunks and walls of root-knotted bank, look harmless at first glance, shallow enough for sunlit silt to glow gold under the surface. But beneath that glassy calm hangs a different kind of quiet, one that hums like a wire pulled tight. Every suspended leaf, every drifting seed, every wavering reflection seems to be watched by something just below, something that barely moves, yet misses nothing. The piranhas are waiting. They hover in clusters beneath the overhangs, bodies motionless except for the faint ticking of gills and the subtle corrections of fins that let them hold position with surgical precision. Their silhouettes are compact, deep, muscular discs built for sudden acceleration rather than long pursuit. The light catches the edge of their scales, throwing metallic flashes that vanish as quickly as they appear. Their eyes, however, do not vanish. They stay fixed, unblinking, always aware of one another, always aware of the water. The camera drops beneath the surface, and the water becomes a world of suspended particles, drifting pollen grains, crushed leaf fragments, the soft clouding of decomposed bark. In that haze, the piranhas appear carved from steel, bodies taut, jaws slightly parted, revealing teeth shaped like tiny guillotines. These teeth are not curved like most fish. They are perfectly triangular, interlocking like the blades of pinking shears. One bite does not tear. One bite removes cleanly. Their stillness is deceptive. Piranhas are not mindless thrashers, not the chaotic predators of myth. They are patient opportunists, sensitive to the slightest shift in the chemical and mechanical landscape of the water. Their sense of smell is so refined that they can detect the faintest trace of blood or injured tissue from astonishing distances, carried downstream like a whisper. Their lateral line, an aquatic sensory organ tuned to vibration, runs along their flanks like a second nervous system, alerting them to movement far beyond their visual range. A single panicked kick from a struggling fish can broadcast across meters of water, traveling through the channel like a flare fired into the sky. It is not violence that wakes the swarm. It is information. The moment arrives quietly. A frog slips from a log, misjudges its landing, and hits the water with a muted splash. For a second, it swims confidently, limbs working in coordinated bursts. Then, a trailing reed cuts its flank, opening a shallow wound. Hardly anything. A thin thread of blood blooms from the scrape, unraveling into the current like smoke pulled apart by wind. And the piranhas feel it. The closest fish tilts its body slightly, letting the plume touch the sensitive pores around its jawline. The information is undeniable. Fresh blood, mammalian or amphibian, warm-bodied, small. A viable target. That single physical cue triggers a behavioral cascade. The nearby piranha snaps its fins once, twice, rising from its hover. The others register the motion, then the chemical signal, and begin to converge with the precision of synchronized swimmers. No sound. No frenzy yet, just a tightening of formation. The frog kicks harder, confused by the sudden tension in the water. The vibrations spike. The swarm ignites. Piranhas don't charge as one chaotic wave. They arrive in pulses. First a small group that darts in, testing the prey with lightning-quick nips. Each nip removes a sliver of tissue, a piece of skin, a strip of muscle, a fingertip-sized gouge. The frog jerks violently as pain floods its nervous system. That jerk creates more movement, more vibration, more distress cues. The second wave arrives, then the third. The water erupts. In less than 3 seconds, the frog accumulates half a dozen wounds. None are deep on their own, but each one bleeds. Blood spreads like a dye cloud, thickening the water around the prey. This is what the swarm is built for. Openings. Multiple wounds close together increase chemical signal intensity, pulling in fish from farther down the channel. The frog's blood pressure collapses as capillaries rupture faster than they can clot. Shock sets in almost immediately. As the frog weakens, its movements become erratic. Erratic movement is the piranha's trigger for full commitment. Now the bites change rhythm. They become systematic, efficient. The lower jaw of each piranha anchors, the upper jaw slices down like a paper cutter. Small pieces of flesh vanish into armored gullets. A delicate bone structure, finger-sized limbs, breaks under the pressure. The frog stops kicking. The swarm doesn't stop. The camera pulls back to reveal the frenzy from above. A churning storm of silver bodies and red plumes, a biological grinder that erases the boundary between life and death with terrifying speed. But then, almost as soon as it began, the movement slows. The pieces shrink. The cloud fades. And finally, the swarm disperses. What remains drifts downward. Bones stripped white, tendons floating like translucent threads. A few air bubbles rising from tissues no longer intact. Within the ecosystem, nothing about this is chaotic. This is processing, recycling, enforcement. Despite their grim reputation, piranhas are not monsters. They are regulators. They clean the river of carcasses before decomposition can poison the water. They cull the weak, removing diseased or injured animals before those animals can spread pathogens. Their feeding frenzies, though brutal, maintain the health of fish populations by preventing overcrowding. Their role is not destruction. It is balance through uncompromising efficiency. Capybaras that enter the water injured from jaguar attacks often become targets within minutes. Birds with broken wings that fall into side channels are claimed almost instantly. Even caimans are not immune. Juveniles with open sores or old injuries sometimes vanish in short, violent bursts of silver. The piranhas don't chase them. They simply wait for weakness to declare itself. But their adaptability goes further. Piranhas communicate through sound, tiny clicks generated by muscles near their swim bladder. These clicks escalate in frequency during feeding and frenzy, coordinating the spacing between individuals so they don't injure one another. Even in chaos, the swarm organizes itself to maximize efficiency and minimize unnecessary harm within the group. In drought years, When water levels drop and fish become trapped in shrinking pools, piranhas often turn to scavenging rather than active hunting. They feed on dead fish first, avoiding conflict until absolutely necessary. Their aggression is situational, not constant. When food is plentiful, they conserve energy. When food is scarce, they enforce a brutal hierarchy. The rule becomes simple: the weakest becomes the resource. The camera shifts again, this time showing the aftermath. The side channel looks peaceful, almost serene, as if the water itself is incapable of violence. A few leaves float on the surface. Small minnows return to the edges. Somewhere deeper, among the submerged roots, the piranhas resume their hovering positions, motionless once more, waiting. The forest above continues its rhythms. Howler calls rolling across the canopy, macaws cutting bright streaks through the sky, insects beginning their twilight chorus. But beneath that vibrant layer, the river keeps its own law. A law enforced not by stealth or poison or constriction, but by numbers and teeth so sharp they carve through flesh like wet clay. In the Amazon, predators announce themselves in many ways: the roar of a jaguar, the splash of a caiman, the slow coil of an anaconda. But piranhas deliver their message differently. They whisper through water, through chemistry, through the shared instincts of a school tuned to the slightest sign of blood. And when that signal arrives, the river answers with a swarm that leaves nothing behind, a swarm that listens for weakness, a swarm that never misses the call.